Okay, so today we're going to go over section 10.4 and we're going to talk about retirement savings. We've talked about how to deposit money and watch it grow using compound interest, but today we're going to talk about a different type of retirement account. Okay. So we've already done this problem or something like it. Suppose you receive an inheritance of $50,000 into an account that pays 8% annual interest, compounded annually. What will be the future value of the account after 30 years, right? And so then you have to know which formula you're going to use. And so here we're going to use the formula that F, the future value, will equal P, the principal value, times 1 plus R raised to the T, right? And if you remember, what you can look at is T is going to be the number of compoundings. T will equal the number of compoundings. R will be the growth rate per compounding. And then P will be the principal, or the initial amount. And then F is the future value. Okay, so in this case, we're depositing, the number of compoundings. You're doing this for 30 years and it's compounded once a year, so you are going to compound this 30 times. This is annual interest rate of 0.08. The principal is $50,000, so you receive an inheritance. And rather than going and buying that brand new car, you decide to invest the money for retirement, and your future value is what we don't know. Okay, and so then F is what we don't know. Your principal is $50,000. Your base becomes 1.08. Do that arithmetic in my head. 1 plus 0.08 is 1.08. And then T, number of compoundings, is 30. Then this just becomes a matter of punching this into the calculator. You need to figure out how to use your calculator, because how to use exponents and things of that nature. 50,000 times 1.08 raised to the 30th power. This is going to be very important. You're not going to want to do this on your own, right? Or by hand, I should say. $503,132.84. So instead of buying that fancy car, you decide to be responsible and invest your inheritance, and you get $500,000 for retirement after 30 years. Your $50,000 grew. Now this is a very good example of a retirement account. But some obvious drawbacks to this is, not everybody has $50,000 to invest right away, and so if you're waiting to accumulate $50,000 to start your retirement account, you might be waiting for a while. So a better thing is to make a much smaller payment, and that leads us to today's lesson. We'd already done this, but I wanted to give you a reminder of what we have done. So here's what we're working on today. You get your first full-time job. Your plan is to deposit $1,000 at the end of each year for retirement into an account that pays 6% annual interest, compounded annually. So your plan is to work for 30 years. What will be the balance in the account at the end of 30 years? So what's going on different here is that your plan is to deposit $1,000 at the end of each year for retirement into an account that pays 6% annual interest compounded annually. So you're going to wait till the end of that year to accumulate that $1,000. And once you have that $1,000, you're going to put it into the retirement account. From then you're not going to touch it, and it will accumulate interest for the remainder of the time. Okay. So again, what you have here, since you're going to make 30 deposits, you have 30 problems where each problem looks like this. We called this F, is equal to P times 1 plus R to the T. Right, but you have 30 of these problems because you're going to make 30 deposits. So you can look at each deposit as a separate investment, and each one is going to sit in there for a separate amount of time. Right? And so the key here is that you're going to have 30 deposits. And so let's call D1 your first deposit that you make at the end of that year, and it's going to be a $1,000 deposit, but it's only going to sit in the bank for 29 years. So the future value of that deposit will be 1,000 times 1.06 raised to the 30th power. And we're just going to leave that alone. Leave that like that. We're not going to figure out what that is. Right? Now, the second deposit you make is going to be another $1,000 deposit. But now, I'm sorry, that's not going to sit in the bank for 30 years. It's only going to sit in the bank for 29 years because you deposited at the end of the first year. So it only sits in the account for 29 years. The next one that you deposit at the end of year 2 is only going to sit in the bank for 28 years. And so that exponent becomes 28. The next one is only going to sit in the bank. It's still a $1,000 deposit. You're making a new deposit. It's of $1,000. All these are going to be the same to keep things simple. But that one's only going to sit in the bank for 27 years, right? 1 year less. And you're going to keep going, right? And I don't want to keep writing all these down because, you know, there's going to be 30 of them. But you're going to keep going. And then the last year, your 30th year, you're going to make that 30th deposit, and it's just going to sit in the bank for no time, right? And so you're just going to put that $1,000 in the bank, and then so it's not going to collect any interest, right? So you have 30 deposits that you make, one at the end of each of your working years, and then the first deposit that you make sits in there for 29 years. The second one sits in there for 28, and so on until you get to that last one. It doesn't sit at the bank for any time, and so you don't get any money in terms of interest for that. But it's going to make our calculations a little easier. So what we want to do is figure out what is the value, and of course then the value is just to add all these up. And what I'm going to do is I'm going to add them up backwards. Right, so I'm going to start with that deposit that sat there for no time, so that would be $1,000, and then I'm going to add the deposit that I made the second to the last year that would have sat in there for 1 year. That would have been 1,000 times 1.06 because it only compounded interest once. And the next one would have sat in there for another 1 more year than that one. And so it will have sat in there for 1,000 times 1.06 squared, and so on, until we get to these last deposits that would have sat in there for 27 years. 28 years. Oh well, let me go ahead and start over a little bit. Can't write all 30 of them down, because then we have 1,000. To the 28, and then plus 1,000 times 1.06 to the 29th. Now there's 30 numbers there, and even with the calculator, this would still take me a while. And I don't want to do all that. So a neat trick is to take both sides of this equation. This is an equation because it has an equal side, an equal sign right there. And we're going to take both sides of this equation and multiply it by 1.06. And you'll see why in just a little bit. Okay. And so when we do that, the left side becomes 1.06 times V. And the right side, this 1,000 gets multiplied times 1.06. So instead of writing it right underneath, I will write it over here as 1,000 times 1.06. This 1,000 times 1.06 gets multiplied by 1,000 times, gets multiplied by 1 times 1.06, and it will become 1,000 times 1.06 squared, and so on. And they will, the one that right before this one will become 1,000 times 1.06 to the 28th, and the one right before, and so this one times the 1.06 will become 1,000 times 1.06 to the 29th, and then the 1,000 times 1.06 to the 29 will become 1,000 times 1.06 to the 30th. And what I'm going to do is I am going to subtract. I'm going to subtract here. And on the left, what I have is V minus 1.06 V, which is then going to make negative 0.06 V. Now on the right, I'm going to subtract vertically. 1,000 minus nothing is still 1,000. 1,000 times 1.06 minus 1,000 times 1.06, those are going to go away. The 1,000 times 1.06 squared minus the 1,000 times 1.06 squared, those go away. And the nice thing that happens is all the ones in the middle go away, and all that's left is this first term, the 1,000, and the 1,000 times the 1.06 raised to the 30th power. Okay. And then what I'm going to do to figure out what V was is multiply both sides by -1 or divide by -1. Let me go ahead and multiply by -1. And then what that is going to do is on the, I'm sorry, oh, I'm sorry, I don't know, I shouldn't have done that. Well, let me go ahead and just do that. Right, and so now what I get is 0.06 V is equal to, and then I'll get the negative 1,000 plus the 1,000 times 1.06 to the 30th power. So I can rewrite that as 1,000 times 1.06 to the 30th power minus 1,000. And then I can divide both sides by the 0.06. Divide both sides by the 0.06. And we get this. V is equal to 1,000 And I'm up on top, since they both have a 1,000, I'm going to factor that out. I'm going to factor out that, and I'm going to get 1.06 to the 30th power minus 1. Factored out that 1,000. And you'll see why I did that in just a little bit, divided by 0.06. And now if we compare this to our original problem, we can see where everything came from. This 1,000, that was how much we were depositing each time. Each time we were depositing $1,000. The 30 came from the fact that we were made 30 deposits, right? So we had 30 deposits, and that's where the 30 came from. If you go through our work, that's where that 30 is going to come from, the number of deposits. The 0.06, that was our annual interest rate, right? And then the 1.06, that's because every time you go through a percent increase, you have to multiply by 1 plus r. And 1 plus r, the 1 plus the 0.06 gives us this 1.06. And this 1 is always going to be a 1. That came from factoring out the 1,000 here and here. And so then this 1 is always going to be a 1. So it didn't matter what our deposits were. It didn't matter how many years we were going to do this for. It didn't matter what our interest rate was. All these different things would work the exact same way. And so rather than doing this process over and over again and having to take all this time, we have this formula. That's the beauty of algebra. The retirement savings formula, annual contributions. Okay, so the final value, V, will equal your monthly payment or your monthly deposit, P, times 1 plus r to the y minus 1 over r, right? That's what we saw. And there's your formula. Here, P represents the annual contribution made at the end of each year. So this formula only works if you are making contributions as we stipulated at the end of each year. There's a different formula for what happens if you make your deposits at the beginning of each year, which might seem to make more sense, but we're not going to go over that. You'd have to tweak this just a little bit, but we're not going to do that. So Y represents the number of years of retirement savings, and R represents the annual interest rate expressed in decimal form. Note, the lonely R in the denominator is what's left after the original denominator. 1 plus R minus R is simplified, right? So R is the annual interest rate. Okay. So find the value of a retirement savings account paying an APR of 5.4% after 40 years. Contributions made at the end of each year, including the last year, when the annual contribution is $1,200, and B, when you only deposit $600. Okay, so again, the formula is V, your final value, will be your P times 1 plus R to the Y minus 1, all divided by R. That is the formula that we are using. So in this formula, in part A, your V is what you don't know. Find the value of the retirement. So V is what you don't know. P is you are making annual contributions of $1,200 starting at the end of each year. Okay. R is our annual interest rate, but again, that needs to be written as a decimal, not as a percent, so 0.054. And then we're ready to go. So V is equal to P, 1,200, times 1 plus R, so we can do that in our head, 1.054, no need to write 1 plus R. We raise that to the, oh, I'm sorry, I forgot the Y. How many years are we doing this for? We're doing this for 40 years. And so then this exponent becomes 40. Minus 1. And that all gets done first. And divided by r, which is 0.054. If you purchased one of the scientific calculators that, one of the graphing calculators that I asked you to buy, if you could, then you can do all this just in one step, and you can punch it in the same way that you see it there. Divided by 0.054. And so then what I get is V will equal 159,92054. And so you will have $159,920.54 for retirement waiting for you. Right? Now, for part B, the only thing that you've changed is now your payment, your principal, how much you're going to deposit each month is now half. It's 600, right? So then same formula, 600 times 1.054 to the 40th power minus 1, all divided by 0.054. And all you have to do is change that to $600, and you get $79,960 and 27 cents. It is exactly half of what you got when you deposited the 1,200, because 600 is exactly half, and the only thing you are changing is the P. And so then your final value, with everything else fixed the same, is directly proportional to how much you make every what deposit you make every month, right? So very common amongst Americans to not save enough and not have enough ready for retirement, and then we procrastinate. That's what we do. And so people always ask when I teach math, what is this good for? So here I can actually give you a good answer, as opposed to just saying, because it will be on your test next Friday. You can see what is going to happen with different retirement strategies, and you can adjust accordingly. Hopefully you can adjust accordingly. Okay, so find the value of a retirement savings account with an annual contribution of $1,200, contributions made at the end of each year, including the last, and an APR of 5.4%. Okay, so what we're changing here is for A, B, and C, we're changing the duration of the time, just to show you that time is critical when planning for retirement. Right, so we have 35 years, 45 years, and 50 years, and we're going to see what happens to our retirement account over these different periods. Okay, so again, we're still using the same formula. V is equal to your annual payment into your retirement account, 1.1 plus R, to the Y, number of years, minus 1, all divided by r. Okay, so in all of these problems, the y is, the p is $1,200. The r is 0.054. And what is changing, the v is what we want to know, and what is changing is the number of years, right? So for part A, v is equal to the $1,200, too many zeros, times 1.054. Now we're doing this for 35 years, minus 1, all divided by 0.054. So we're going to take 35 years less. We're going to take 5 years less. And doing this, waiting 5 years to stop, to start our retirement, will only give us $117,803 and 83 cents. When we did this for 40 years, we got 159,000. So round numbers, we got 160,000 there and only 120,000 here. So we get an extra $40,000 by increasing our time to 40 years instead of 35 years. So for part B, it's the exact same thing. $1,200. But now we have 1.054 to the 45 years. So now we've gone the other way and increase the number of years to 5 from our original 40 from the previous problem, and then divided by 0.054. And again, this is just punching this into the calculator, changing the exponent from 35 to 45. And now, by adding 10 years to this one or 5 years to the other one, we're at $214,705.01. So comparing A to B, going from 35 to 45, adding those 10 years, we almost added $100,000 ready for retirement. And now we'll do part C over here where we have some room, and it's the same thing. All we're changing now is we're changing the number of years to 50. So we have $1,200 times 1.054. Now it gets raised to the 50th power, minus 1, all divided by 0.054. Put that into the calculator. And this becomes $285,967.41. So by adding these 5 years from 45 to 50, we increased from 15 to 85 by $70,000, right? And so the key point of this exercise is one of the most important factors is time. How much time you have to how much time you invest for retirement. If you read the book, you'll see that sometimes that if everything else is fixed the same, if you double your investment, your monthly investment, you don't make up for half the for the amount of time. Um, okay. Now, this is again a little contrived because you're waiting for the end of the year to make your deposit, and then that was just so that we could show you where this formula came from relatively easy. But what's more common in everyday life, or when people do this, what's more common in real life, I should say, not everyday life, is that instead of making your deposit at the end of the year, you make it at the end of the month. It makes sense to wait till the end of the month because you get paid at the end of the month, or most people get paid at the end of the month, and so that's when you make your payment, right? And the only thing that's going to change is this thing here, y, instead of being the number of years, it's going to be the number of deposits. So so y is just going to be the number of deposits that you're going to make, and the r here, instead of being the annual interest rate, which is how things are usually advertised, it's the rate per compounding. How much do you get each time? And so here's your next formula. It's very similar to the formula you had before, but the only difference is, I'm sorry, that was the same formula, right? So looking at this formula, your exponent here is y. That's the number of years, but you're not going to make a deposit every year necessarily. You might make it every quarter or every month, maybe every day, depending on how you're going to do that. So that needs to change, and all that keeps track of is the number of compoundings. Or the number of deposits. And so then this right here is your annual interest rate, but that's how things are usually advertised, and you're not going to get that same for every month. And so here's your retirement savings formula, how we adjust it for the monthly contribution. So instead of P, we're calling it M, and this is your monthly payment. That's your monthly contribution, right? Instead of 1 plus r, it's 1 plus r divided by 12, which we a lot of the times can't do that in our head anymore. So we're just going to have to let the calculator do that. So 1 plus r divided by 12. This is just the rate per compounding, since you're compounding monthly, and it's usually given to you as an annual interest rate. R divided by 12 is the rate per compounding. And T is going to be the number of deposits, right? So here, M represents the monthly contributions made at the end of each month. T represents the total number of monthly contributions. And R represents the annual interest rate expressed in decimal form. So find the value of retirement savings account paying an APR of 5.4% compounded monthly after 40 years of monthly contributions made at the end of each month, including the last month, when the monthly contribution is $100, $50, $150. Okay, so again, you need to write down the formula. M is equal to V is equal to, not M, V is equal to M times 1 plus R over 12 raised to the T minus 1, all divided by R divided by 12. Okay. So I have to figure out what everything is. Find the value of the retirement savings account paying an APR of 5.4%. So you know that your R is 0.054. Compound it monthly. After 40 years, so of monthly contributions made at the end of each month. Okay, so then T, oh, I'm sorry. So for part A, M is $100. We're depositing $100 each time. So M is 100. And what all we need now is what is the T, right? And so then T, you're doing this for 40 years, but you're making 12 deposits every year. So then you get 12 times 40, 480. Go ahead and write that down for you. T is the number of deposits that you're making, or number of contributions. You're making 12 a year for 40 years. 4 times 12 is 48. And so you get 480. And so then you get that your V is what you're looking for. And that will be your $100 times 1 plus, can't do the 1 plus R in my head anymore, so I just do 1 plus 0.054 divided by 12. And we're going to raise that to the 480. We're making 480 deposits. Minus 1 divided by R divided by 12.054 divided by 12. And you can punch this all into the calculator at one time. And so what you get is 100 times parentheses 1 plus 0.054 divided by 12, close the parentheses, raise it to the 480th power, subtract 1, close the second set of parentheses, divided by, and you want to divide by that fraction, so you want to hit divided by, and then parentheses, 0.054 divided by 12. And when you hit enter, you get $169,538.30. Now in part B, the only thing that changes is now you're only making half the contribution, and so now your monthly payment is $50, and so then you are going to if you look back, so your answers need to make sense. So we did this at 5.4% for 40 years, and we got $169,538.30. Earlier, we did this at 5.4% for 40 years, and we were only making deposits once a year, and you see that we got $159,920.54. So it makes sense. Our answer seems reasonable, that we got a little bit more, $9,000 more, by making monthly deposits rather than making yearly deposits, giving our money more time to grow. In the yearly deposits, your money doesn't grow until the end of the year. So this gives it a little bit more time to grow. It only has to wait a month to grow. Okay. So for part B, all you're changing is from the 50 to the 100. So V is equal to 50 times the 1 plus 0.054 divided by 12 to the 480 minus 1, all divided by 0.054 divided by 12. And so again, you really should expect that because you're only depositing half the money, you should only get half the return. And the only thing that changes is the 100 gets replaced with 50, and that's exactly what we see. Get exactly half. This is $84,769.15. I won't do part C. There's no room, and it's just a matter of changing that M from 50 to 150. So we'll move on. Okay, so now that we have a formula and we know how to use it, we could look for other things. All we've been looking for is the final value, but we want to do some planning, right? So this question looks at that. What should your monthly contribution be if your goal is to have $400,000 in your retirement savings account after 50 years? Assume the APR is compounded monthly and that the contributions are made at the end of each month, including the last month. So again, you have to know which formula you're using. And since we're making monthly contributions at the end of each month, then we're in that formula that we just finished. V is equal to your monthly payment times 1 plus R divided by 12 raised to the T minus 1, all divided by R divided by 12. What should your monthly contribution be? It means we're looking for M. We don't know what that is, right? And so then we know the final value. This is our final value, so we can substitute that in. $400,000 is what we want to have in the account. We don't know what M is. We do know everything else. We know that 1 plus our annual interest rate is the same, 0.054. We know that we have to divide it by 12. And we're doing this for 50 years. So 50 times 12, 5 times 12 is 60. We get an extra 0. So we get 600. So we're going to make 600 deposits. Minus 1. And then R divided by 12. Okay. And so then we get, now notice that this part right here is just a number. So why look at that number and try and do the algebra with that number? Let's figure out what that number is. So parentheses, parentheses, 1 plus 0.054 divided by 12, close the parentheses, raise that to the 600th power, minus 1, close the first set of parentheses, divided by parentheses, 0.054 divided by 12. And when I hit enter, the calculator tells me that this is 3,064 and 42 hundredths. And so then this is just a basic trying to get the M by itself. So to get the M by itself, since we're taking M and multiplying it by 3,064 and 42 hundredths, we just divide by that. We divide both sides by that, 3,064 and 42 hundredths. 3,064 and 42 hundredths. We get our value for M. So 400,000 divided by 3,064 and 42 hundredths. M is $130.53. So if you have an idea of how much you want for retirement, you can do a little bit of algebra and figure out, hey, you need to save $130.53. You could then include this in your budget and make sure that every month you take care of this, like if you were taking care of any other bill, whether it be a power bill or whatever bills you pay, you know that you have to pay this $130.53 to your retirement, so that when the 50 years come along, you have the $400,000 to retire on and make your life a little more comfortable. Your homework for this section is 45 through 53 odd. I will host a conference on Wednesday at 6 to answer any questions that you have on this section. When I host these conferences, first I will take care of the previous day's problems, and then if there is time, I will go over anything else that you'd like me to go over. So that's time made available for you, kind of like office hours. Now I'm going to host the section at 6 o'clock. If by 6:15 there is nobody there, I'm going to end it. And you could also reach me by email. Okay, thank you. Have a good night. Stay safe.